when we heated the system consisting of the water in the bottom of a bottle, a stopper in the top of the bottle, a tube leading up to a reservoir at some height h, and we'll quantify that in a minute, or at least symbolize it. We started at room temperature, which in this slightly warm room is about 25 Celsius or 298 Kelvin, 1 atmosphere, and let's assume a 300 milliliter volume of water. Now what's going to happen is we're going to add thermal energy to the system. The molecules in the system will start moving faster and exerting greater pressure as they collide with the different surfaces and with the water and so forth. And things will start to happen, as you well know from having done the experiment. So what happens is we first add enough thermal energy to just raise the water to the top of the tube without having any overflow yet. Now if the height of the tube is delta H above the water level, delta H measured from the water level to the top of the tube where the water level is now, then from Bernoulli's equation we can see that the pressure has to be 1 atmosphere plus rho GH in the bottom. Pressure here is 1 atmosphere. The altitude here is delta H lower. The pressure at the surface of this water, we're actually comparing the pressure at the surface of this water where it meets the air and this water where it meets the air inside the bottle. The pressure in here by Bernoulli's equation has to be 1 atmosphere plus rho GH. Now, we assume that we have thin tubing so that there's negligible volume of water in the tubing. And we're also going to ignore, and this is maybe a little more serious, we're also going to ignore the fact that the bottle itself, and therefore the volume in the bottle, increases a little bit when we heat the bottle up. There's actually a significant change in the volume of the bottle, and that would have to be taken account of to make this experiment really precise. Nevertheless, we're going to make a first approximation and say that the volume of the bottle remains constant. The volume of the air inside the bottle also remains constant because very little water goes up the tube. The water level therefore doesn't change very much. Since the volume and the number of moles of the gas therefore remain constant, the number of moles remain constant because everything's sealed, the temperature is going to be well, the ratio of temperatures will be the same as the ratio of pressures. This means that the temperature to which we raise the water is going to be the ratio of the pressures times the original temperature. The original temperature is 298 Kelvin. The pressure ratio is 1 atmosphere plus rho GH to 1 atmosphere. So this is going to be the temperature in this state. Now later we'll number these states and be very systematic about the process, but right now you need to see that the pressure has to go up to get the water here. The temperature has to go up to increase the pressure. And the proportionality is the simplest one because volume and quantity of gas, the number of moles, are constant.